Hi, everyone. So we will start as usual at 11:10. One question, would I go over the question 2 from last quiz today? Yes, I will. That's the first few slides will be about that, so don't worry. While we're waiting, guys, if you had some generic questions, you can post them in the chat. Similar to previous weeks, when the class starts, if at least some of you can periodically turn on your video, that would be really great. So I can see you and at least I can see the reactions to things, right? But I'm going too fast or too slow. Like you don't need to run it all the time, but if you can do it at least part-time, that's good. What is the image of the bottom right? Oh, good questions. I like the questions. Anyone can say what it is? I didn't put a logo there, but maybe you can guess by looking at the colors. Oh yes, Sam said correct. That's TPU version, I think the version 3 actually. So for people who don't know, the companies like Google and Amazon are building dedicated hardware for machine learning. I guess a lot of you've heard about the importance of machine learning these days. So the volume of compute is so tremendous, so they started to build dedicated chips. This is the third iteration of the chip from Google. They had like the fourth generation right now, but it's still in experimental phase. You cannot buy them, but you can rent them in the Google Cloud if you want to run experiments. For example, my group does a lot of research on machine learning and hardware. So we had, and Google provided us access to 512 of those TPUs, which are quite expensive. So we do run some research on them. And on the left-hand side, you have the latest and greatest of the NVIDIA GPUs. That's also used for machine learning, but not only. It's used for high-performance computing. It's used obviously for graphics, so you can play games on this thing as well. Although this chip's a little bit expensive for gaming, it's probably around 10,000 US. And no surprises, all of these chips are built based on the concepts we are covering in this class. So it's like they don't use any other special, technology. It's all CMOS-based technology. The transistors you're learning right now, they use there. Today we're going to talk about adders, multiplexers, comparators. Pretty much all these chips are built out of these basic units, right? They're more complicated, obviously, than that, but they all build of this primitive logic gates. Any other questions before we start? Okay, so let's start. So it's week of 3 of this class. So hope you guys still enjoy it. I see we lost some people in terms of attendance, but hopefully it's not because things are available online or I'm too boring. So hopefully you still enjoy and learn something from this class. Again, just a reminder, please turn on your videos if you can. That would help me a lot to see the speed, because especially today, we're not going to have as many slides as before, but slides will be more complicated. So looking at you help me to understand whether you understand it or not, or how puzzling is the material there. Okay, thanks a lot. Okay, so I got a lot of requests about that. So let me clarify it. So we had the first quiz, right? Last Friday. Was the first time we were doing it online this way. Things went reasonably well, but not perfect. And there's one thing that I'm gonna specifically clarify. So I'm gonna talk about question 2. You see the statistics for these questions and the answers for it. So the main focus of what we're doing here is the question was about impurities to the semiconductors, right? And what does it cause? So I first explain you what should be the right answer. Then I'll explain you, I guess, where the most confusions are coming from and how we're going to fix it. So the main reasons why the impurities to the semiconductor is added is really to create electrons and holes, right? That's the most deepest answer you can get to that, because that's really the primary goal. That's what happens at the lowest level, and that's this is how well you can understand it at this point of time. This is what really happens. There are answer number 2 and number 4 are really just completely wrong. So it's neither it's positively negatively charged, it's neutral, right? And there is no increase in resistance in the semiconductor. So the problem happens from the answer number 1, so instability in the semiconductor. Let me explain why it won't be fully correct to call semiconductor unstable. Let's see if there's any questions here. Okay, guys, please focus on the class right now. Okay, so so when we say something is unstable, like the real unstable material is the material that's going to do something if you don't touch it. So for example, if you have uranium, right, in nuclear reactions, it's unstable by itself. It's going to emit electrons and protons and other stuff, right, by itself, even if you don't touch it, right? So this is what real instability means. What happens in the semiconductor is a little bit different. We make it, it's still stable. So we had a spring with the weight. It's after it's stabilized, it's stable, right? But it's easier to move it from an equilibrium state, right? So you wouldn't call it completely unstable, right? But it's easier to move it from the stability rate. So in that sense, I guess my mistake in the class was saying that you make it a little bit more unstable. It's not the correct wording. So essentially what should happen in this question, and I missed it when the TA make the question. So instead of select all that apply at the end of the question, it should have select the best what applies, right? And that would make it clear, and most of you probably would answer it correctly. So I believe this is mistake on our side. So what we're gonna do with this is essentially losing one question like that. It's something a little less than 0.2% of your grade. So if it's gonna ever affect your grade at the end of the class, we're gonna add it up. And we are trying to not make any further mistakes, but if they will happen, we will handle them the same way. So if we generate a question that's not completely clear or there is some confusion, you will get the grade for it right at the end. We're not going to fix it right now because it's a lot of manual labor for TAs to go and fix every single, person, like out of 97 responses here. But don't worry about that. That won't negatively affect your grade. But the main thing I want to focus right now, you do understand the correct answer. You understand where confusion is coming from and what the right answer is, okay? Because the main thing you would understand now where the difference is coming. So it's instability in the semiconductor is just not complete. It's not completely incorrect, but it's not the right word to call that material unstable. It's just, it's easier to move it from the equilibrium state. So it's not as, as good as in other cases. Okay, any questions? So could you repeat what the instability word means? Okay, Sam, did I answer your question? Okay, good. So yeah, so this is where there, you need to distinguish like a completely unstable material. It's something either say positively or negatively charged. So they're definitely gonna attract electrons or emit electrons, or something that you use like a material in the nuclear reactors that can, emit particles by themselves. This is unstable. So if you leave semiconductor alone and don't apply charge to it, it's going to be stable. It's not going to emit electrons. It's not going to change its state. But it's easier to change its state in a nice way if you apply something to it. Okay, I hope we've figured it out. I hope no one feel, confused anymore. And I think it's clear how we're going to handle if we make some mistakes on our end. Okay. Okay, let's move on. So where we are. So we talk about transistors, we talk about gates and circuits. It's time to talk about more advanced things. Let's talk about devices. So we want to build something larger than we build with like and or all cool, but we want to do something larger than that. And obviously we learn about how to build devices out of circuits and logical gates. Everything we learn about K-maps will be useful today. You will see we didn't learn it just to test you on a quiz. It's actually a very powerful mechanism to generate new devices. Okay, what we're going to talk to today is logical devices, and we're going to build them from ground up. So we are going to build several different more complicated structures. As I announced, I use everywhere in any chip you can imagine right now. So we're going to start with something called multiplexers, relatively simple unit, but very widely used. So every time in the future when someone's going to propose something in their hardware and you would need certain number of multiplexers, you would know how they're built, you would know what their cost is. Obviously, we want to build an adder. That's the most popular operation you can imagine that's used, right, in computing. So we're going to build an adder today with you ground up. So whenever in the future you're going to use an 32-bit adder, right, or 64-bit adder today you're going to see literally how it's built out of which logical gates. So it's not going to be a miracle to you anymore how the AND is built, right? And how all this logic, where it has sign, how the subtraction is done as well. You've seen a little bit of this if you use C language before, but that's going to be really now opening to you, because now you're going to see every little bit on how it's done. So you can think about all the way from electrons into how I build an adder, right? So at least you would understand if you run an assembly instruction, right, or any instruction in C code, you would really understand how it works. Then we're going to cover subtractors. You will see that subtractors actually can be nicely done out of adders. So you don't need to build a special logic for subtraction. You can just use adders with just a little bit of smartness in it. Then we're going to show you how to build different types of decoders. And hopefully, if time permits, we're going to talk about comparators. If time won't permit, then again, we will talk about this on Friday. Okay. So again, as I announced, the further lectures are going to have fewer slides, but slides are going to be more dense and more complicated. So I expect you to be actively participating, asking questions, right? Again, like try to be reasonable, but so we can finish on time. But at the other end, if you're really confused or lost, ask questions in the chat. I'll monitor chat and periodically going to batch process the questions. Okay, let's move on. So what are the multiplexers? What are those things that you probably heard before, and what does it really mean? Okay, those are logical devices that are very common to many different circuits and have block elements of their own. So multiplexers are, or the full short form for them is called MUX, right? That's what most people that study engineering or CS, that's how they call them usually, MUXes. The behavior of this thing is very simple. So you have two inputs. I assume you guys can see my mouse, right? Right. You see, so there is this circuit here. We have X input and Y input, right? And then we had another side input, sorry. And that side input S can either 0 or 1 as everything here. And what it does, it allows us to select which of the output I want, which of the input I want to take as an output, right? So essentially, if I had 0 in my S bit, then output is X. If I had a Y, so if I had S equal to 1, then I'm going to take Y input as my output. Okay, so this is really just selecting which input that goes through. The best way to think about it, there is this magic switch going up or down, right? That either connects to this guy, so this input goes through, or if this input goes through. Okay. Again, remember, this is not a real physical implementation. That's the best way to think about it logically. You either connect this channel or this channel. Okay, but we want to build it out of transistors, out of the logical gates, right? What's our mechanism to do it? Anyone want to suggest me something before I show you how we're going to do it? So this is logically I want to get, but what's our mechanism to make it formally, mathematically? How we're going to design logic? Yep. So K-maps, Terry, it's a bit too early to K-maps. Before you go to K-maps, what are you going to do? You would need K-maps eventually, but what's before that? So what's the first step? Truth table, absolutely correct. So I just described M gate is not, M is an output here. So, okay. It's an M, which stands for multiplexer, right? So it's an output of the multiplexer. It's called M. Okay. So yes, the first thing we do, we take this informal definition that I just say in words and kind of show you the rough diagram, but without showing what is inside this box, we're going to formalize it. How we're going to do it? Truth table. So we had 3 inputs, X, Y, and S. No matter how I plot it, from the logical perspective, they're all equivalent. So an M is my multiplexer output. So the first thing is how we're going to fill in this table. First, X 0, Y 0, right? S is 0. So it doesn't really matter what the Y is, right? I'm going to select the X. So same, so here, if S is 1, I'm going to select Y. Y is 0, and so on, right? Again, I look here, S is 0, so I'm selecting X. Here, I have S1, so I'm selecting Y to be 1, and so on. I think the way I fill in this table is clear, right? So for each value of x and y and looking at s, I either select one or another one. So this is the truth table we got. How are we going to simplify it? I don't want to write it naively. Well, our favorite algorithm, K-maths, right? It helps us, so we learn it on purpose. We're going to keep using it every single time for most of the simple designs. So the way we split things, we have x not x here and y and s on this end. And we do our usual thing, right? We're going to try to form pairs. It's relatively straightforward here. That's one pair, that's another pair, right? Okay. And surprise, surprise, if we just look at that, that's our output. Y multiplied by s, y and s, plus x and s naught, right? So that's essentially that we got just on just looking at it. Yes, you could probably guess it by looking at the truth table, but we don't like guessing, right? We want to have a strong methodological way to generate this thing, right? So this is what we get here. So how we're going to design it? We're going to look at this guy, right? Y and s plus x not s. So that's what we're going to do. This is my input x, y, and s. There is one AND block here. So for s and y, so this. So I use an AND transistor here, an AND gate, sorry, an AND gate. And then I also had x and not s here, so I build it, right? X and not s, this is inverter, not. So this is another AND gate. And then I need to do plus for them, which means OR. Is this clear to everyone how we just build it? And as you know, our favorite gate is what? So what we want to convert it to. So what is our favorite gate? Anyone wants to type it? Yes, yes, you guys remember it, ND gate. How I'm gonna do it? Morgan's law, right? It's not complicated. We all learn it on purpose. So what we're gonna do, we do our usual trick. I'm gonna inject two nodes here, right? And another pair of nodes here, then go make them through. So it becomes an NAND gate, and these two will be NAND gates as well. The usual trick we used before. So overall, if someone says you, what's the roughly the complexity of multiplexer, you can now look at this design and say, you know what, it's 3 NAND gate and 1 NOT gate, right? So you literally know how this multiplexer is built, right? Out of the basic, the most primitive blocks. So where the multiplexers uses, they use very widely, so they're very useful whenever you need to select from multiple input values. Surveillance video monitors, digital cable boxes, routers, all like there are plenty of hardware at home right now and in your laptop that's using multiplexers, right? That's a very popular block, and their key gates, it's very simple, right? 3 NAND gates, right, and 1 NOT gate. It's very simple, okay? Obviously, for multiplexers, there are inverse logic called demultiplexers. So demultiplexers do the same operation, but in reverse. We get a question. Are logical devices just useful circuits? Good questions. I think the short answer, informally, yes. So there are infinite, or not infinite, I think it's a discrete math. There are exponential number of circuits here, right? Possible to build, but we don't care about all of them. We care about the one that actually makes something useful for us. So we're gonna build something that helps. And obviously, engineering and science build on their previous areas, on the shoulders of giants. So there is algebra already, mathematics, right? We know the primitive operations we want to use, add, subtract, multiplications, right? So those are the first candidates we want to implement, right? So obviously, we're going to focus on those, right? So we don't look at all possible functions. Okay, so their multiplexer operation is literally just work in reverse, right? So it looks at the outputs, it looks on the encoding and then selects one of them as an input. We'll show later. So essentially they use as a pair. So multiplexer, so you had multiple inputs, right? Multiplexer, and you can do it not for a pair, you can do it as many as you want, right? Because you chain them up, right? Or make them in a tree fashion. So essentially multiplexer selected one of that, right? Demultiplexer take one of the output of the multiplexer, one conversation selected, so essentially the code for it, right, that output, and convert it into the original input, right? That's what demultiplexers does. Okay, and I'll show you like, you know, how it's used when we use different types of decoding logic. Okay, before that, let's talk about thing that a lot of you probably expect to learn from this course is how the adder is built. To be honest, until I learned something like similar to this course, I always thought about adder as being like some virtual instruction. I thought the adder is built on its own, right, out of some primitive logic when I was an undergrad, until I actually learned how it's built from essentially the basic and and OR logic. Okay, we're gonna build it gradually as well. Nobody goes and build a 32-bit or 64-bit adder from scratch. We're gonna build it one by one. So to build it one by one, we're gonna start, no surprise, from a binary adder, because that's the easiest one. So it's a very small circuit device that can add two 1-bit numbers, and they combine together to create an iterative combinatorial circuits and add multiple bit numbers, right? So we're gonna learn a few different adders: half adder, full adder, and ripple carry adder. So this is what we're gonna focus for the next 30-40 minutes at least, right? This is 3 different adders we're gonna learn right now. And then there will be also carry look ahead, CLA. Okay, before we go into that, I think I would need to review a little bit of binary math with you, because I'm gonna use some terminology some of you might forgot or not absolutely sure about. So the first step is, remember, we as humans like to use decimal numbers, right? That's our favorite systems. We learn to do it, but computers use binary, right? Hope a lot of you know about that. By the end of this course, you would actually deeply understand why computers prefer binary rather than decimal, right? But for now, let's just take it for granted. So if I say a number 258, what it really means mathematically, you had 2 hundredths, or 10 power 2, plus 5, 10 power 1, or 50, plus 8 multiplied by 10 power 0, which is just 1. And essentially, each coefficient between each power should be less than the base, which is 10. Okay, this is the decimal numbers. So how do we deal with binary numbers? So the binary numbers are written this way, and to make sure people avoid confusion, because that number might be also in decimal form and things like that, we put a lower index here. So 2 means that's in the binary format. I hope you guys remember that, or if you're learning it right now, I hope it's clear right now. So if I had something like 01101, a 5-bit binary number, what it means is 0 in front of 2 power 4, plus 1 in front of 2 power 3, 1 in front of 2 power 2, and so on, right? So this is what it really means, which if we compute all of that and convert into a decimal form, that becomes 13 in the decimal format, right? So this is how the binary format looks like. Any questions here? Like, should I go a little bit faster? Okay, this is the binary format. Okay, so how we're gonna do a binary addition, right? So let's first practice it by hand, and then let's build a circuit that can do this magic for you. So first of all, if I want to add up 27 plus 53, I need to convert them into binary form. Don't do it manually right now, just trust what I'm showing you here. So the binary form for 27 is this. It's 3 zeros up front, 1 1 0 1 1. I'm showing these leading zeros because usually we don't use random number of bits. So things are power of 2. So you either had 8-bit representation or 16-bit representation or 32. So this mimics the 8-bit representations. And this is the presentation for 53, 53, right? 0 0 here, 1 1 0 1 0 1. So then we do the addition, right? How we do the addition? We do the addition as we do in decimal, right? We do 1 by 1, right? But remember, it's a binary logic. So if you add up 1 and 1, you're going to get 0 here, and you get a carry bit, right? The carry bit that goes up there, okay? So here you get another carry bit plus 1, so you get 0, another carry bit. Here 0 plus 1 by another carry bit, it gives you 0, and 1 goes here. So this is the way it's implemented, right? If you do it step by step, that's the number you're gonna get, right, at the end, okay? So which is not surprising, would be 80, right? So if you add up numbers that don't fit into 8-bit representation, you might get an extra carry bit that doesn't fit into 8-bit, right? So what it really means that the sum of these two values doesn't fit into maximum possible in 8-bit, and you get this carry bit. And you need to handle it properly, or this information will get lost. So if you just do that and you don't handle carry bit, that would be your answer. So essentially the addition in the 8-bit precision, that bit will be lost, right? And you're gonna get this sum, right? So it would be less than if you would think about it as being infinite numbers. So this is how unsigned binary addition works, right? It might generate your overflow. You might need to handle that, but if you don't handle it, that's the sum that you get. Any questions about that? So if you fit within the format, the sum is the same that you would think in math. If it doesn't fit in the format, you would get it truncated. You essentially get lose the bit. So essentially, this bit really represents 256 that doesn't fit into 1 bit. So you lose this 256. So the sum you get here won't be the real sum. It's going to be the real sum minus 256. Okay. Okay, so this was the repetition of how we do binary math. Then we're not going to go all the way to this. We're first going to deal with just 1-bit numbers. So the half adder is going to be the logical device that had 2 1-bit numbers as an input, and it's going to produce 2 outputs. One is a 1-bit sum, and another output is a 1-bit carry. So let's look at our circuit. So let's look, first of all, what do we build logically? It has 2 inputs, 1-bit width binary adder that performs the following computations. And here, this is essentially what we're logically trying to get. We get x plus y, and we had 2 bits of output. One is s, that stands for sum, and one is c, that stands for carry. And this is how we draw it: 2 inputs, h and y, one main output, sum, and another output that we draw to the side. And that's not a coincidence, because the carry we would want to use, right? You probably already feel what I'm going to do with these units later. So there's not a coincidence I draw the carry to the left side, right? This is a half adder. So what's the logic here? If I get 2 zeros, I'm going to get 0 and 0 for both sum and carry. If 0 plus 1, going to give me that. 1 and 0, going to give me that, the same sum, right? No surprises, right? Commutative. And 1 plus 1 is going to get me 0 as a sum, but then a carry bit. Okay? So the sum is expressed as a sum bit S and a carry bit C. That's how we explain it. This, what it's done logically. So that's essentially what we do. But the question is, what are these logical operation I'm going to do there? Okay, so what was my next step now? So how I'm going to build a circuit for that? What's the first step?
Truth table?
Yes, that's correct, truth table. So I'm skipping the step. That's something you could do it, right? This is just the answer because it's relatively easy. So the truth table is very easy here. So for carry, it's just AND X and Y, right? It's very easy to get. And for sign, if you're going to use the truth table, you're going to get X and not Y plus not X and Y, which logically means just XOR, right? So I'm just simplifying it for you. You can get it even without kernel X because it's simple. But remember, for everything else, we use truth tables, right? So how are we going to design this chip? Well, that's essentially what we build, right? We had inputs X and Y, right? Some of this needs to get from not, right? So you're going to get this one and essentially this one, right? So this is S and this is S. So as you can see, the half adder really needs, we're not optimizing it yet, right? But you see 3 AND gates, right? And you see an OR gates, and you can do our usual tricks with, you know, NAND gates and De Morgan's law. But you roughly get how complicated it is, right? It has 2 negations, and it has 3 AND gates and 1 OR gate. Okay, a half adder outputs a carry bit, but does not take a carry bit as an input, right? So we try to modify this a little bit. We try to build something called a full adder, right? So half adder handles 1 bit, but it's not useful to build something complicated out of it, right? Because it doesn't take any side inputs. So we want another carry bit that can go, you can guess, from another adder potentially as an input. So what is the full adder like? It's very similar, except it has an extra input Z. Sometimes this is also called a CE, right? And a carry in, and this C is called carry out. That's another name that people sometimes label those circuits. So how does it work? When Z is 0, the unit behaves exactly as a half adder. So if that's 0, there are no difference. If Z is 1, then we would need to build the logic and look at it. So any questions? No questions? Okay. Sorry. So you see, so when Z is 1, that's what you build. So essentially, Z is an extra carry that affects your sum. So essentially, if you had 2 zeros and you had Z to be 1, that it increases the value of sum. If it was 0 plus 1, that it makes it 0 and the carry on. So it essentially adds up another 1 everywhere, right? And you treat it as a regular addition. So you see this circuit already gets a little bit more complicated to write things without corner maps, right? So what we want to do is essentially draw the truth table for it, which is not difficult. You see, this is just a regular addition, right? 3 zeros, everything is 0. 1, 1 here. It means that the carry would be 0, but the sum is 1, the same here. And if you get 2 1s, then the carry gets 1, and this becomes 0, and so on. It's relatively simple. Then we build, essentially, start to build the corner maps, K-maps for it. So we get essentially ones here and ones here, right? So the way we do, so essentially you get 1 pair, another pair, and a 3rd pair, right? So we get 3 pairs here, right, to cover these 4 bits. This is to handle the output C, the carry. And this is to handle the output S. Because we have 2 outputs, I need to draw a truth table for both of them. I just put it as just 1 truth table, and I would need to build a circuit for each of both C and S. So here again, I had 4 disjoint ones. So again, I'm not going to show all the logic for simplifications, right? You can follow the usual way to get it, and that's what you're going to get. So here, I guess there's no surprises. It's X and Y plus X and Z plus Y and Z. That's your carry, right? It's all pairwise combinations added up. This is your sign, and then matches all these pairs here, right? So this thing is a slightly simplified version that you would get if you just directly go all the 4 different notations there just by applying some simple logics here. But essentially everything is just XOR X, XOR Y, XOR Z, okay? But you can get it everything using kernel maps plus some simplification from the rules that we learned. Okay, that's what you're going to get if you don't care about each of these circuits. If your goal is just to optimize a single circuit. But remember, I want to make 1 full adder, so C and S is built together. Since they're built together, I want to do cross optimization. So it's not the goal is only minimize this separately and this separately. I want to minimize them both together. How we can achieve it? Well, one way to achieve it is to try to get part of their computation that would be similar to what I have here. So one way to do it here is just you're going to use this thing, right? And simplify it to have the X XOR Y and Z. And essentially, that would allow us to reuse X XOR Y in both here and there. So we're going to build this circuit. I can reuse this unit. I'm not going to write it twice. This is a beauty of cross-optimization. If I'm building a circuit with 2 outputs or 3 outputs or 4 outputs, I not only try to optimize it for a single one, I'm trying actually to optimize it for all of them. Okay, I think I got a question.
Yeah, I have a question. So for the bottom left box, why is it XOR? If you're factoring out the Z, why is it not just regular OR?
Yeah, it's just, it's also OR, but for this point, if you actually do the math, you would see it's also equals to XOR, right? So it's not just OR, it's also XOR. And we're trying to get, like first, if you do this, you get OR first, right? But then you try, and you see that for these cases, because of this extra term, right, it's going to equivalent not only to X or Y, it would actually be equivalent to that. Because what's happened if the only difference between XOR and OR is in 1 bit. And that's where X and Y are both 1s, and that's already 1 here, right? So it doesn't matter what's there. So this is equivalent circuits. You cannot do that from just these 2 terms into this term. You need to look at the whole equation. Is this clear? Yes, so Sam mentioned, I mean, X and Y covered by XY. Yes, that's correct. So how to do cross-optimization? To be honest, there's still a bit of art, right? That's not as straightforward as K-maps, right? This is essentially, in many cases, as far as I know, I'm not taping out new hardware myself, but it's done somewhat manually. So there is still a human that involved in the loop that try to do cross-optimization that group different circuits. That's not an easy thing. It's just, it's combinatorial explosion of possibilities of different things you can apply. So people just look at how similar those terms logically, and they try to count some similarities. I'm just demonstrating it to you. You don't really need to get it yourself, right? But you see how it works, right? What I'm trying to do, I get 2 optimal formulas for each of them, right? And then I'm trying to find some commonalities between them, right? And in this case, I kind of enforce this commonality. Instead of using OR, I would look, because I had this term, I can actually make it to look similar to this term, okay? So the short answer, there is no systematic way as with K-maps, right? It's similar to how you solve calculus problems. You look at some transformation that would help you. But the good thing, we're not going to do a lot of that. Like you're going to do some of the tricks for relatively simple circuits, and then they all build out of this. At any point of time, you don't need to optimize hundreds of those, right? You always build out of a few basic blocks, then you get a bigger basic block, and then you optimize across them. Okay, any other questions? Did I answer everyone? Yeah, for lab 2, I guess you need to follow the handout. So it's better to do essentially what they ask for. And sometimes they want to verify your logic. So I would, if you want to do cross optimization, I would do without optimization and then another version with an optimization to solve the work, right? I'm pretty sure if you do, like you already know how to do it with optimization, you can show both and your TAs will, you know, appreciate that, okay? Okay. So let's go back to the full adder design. So remember on the previous slide, we get this S equals to X XOR Y XOR Z, right? The C term can also be rewritten this way that we just show you. And I think I explained you how I got it. So those 2 terms come from this. X and G, this is called carry generator, just G, where essentially X and Y generate a carry bit. And X XOR Y, they generate something called carry propagate, or P. So essentially it's decide whether the carry will be propagated or not. So this is just a notation, really all the math there is just the names people come up to simplify things. But essentially this is how the circuit would look like. Okay, yeah, there is some, you know, engineering work with internet goes in my condo, so I might get cut out sometimes. So hopefully I'm back. Can you hear me guys now? Can you guys hear me now?
Yes.
Yes, we can, sir.
Okay, so sorry about this. There is some engineering work goes in my building, so they turn on and off internet, and it takes time until I switch to the mobile network. Okay, so let's go back here. I think everyone's seen this, right? So, so this is the circuit we're gonna build for an adder. So essentially, you see there is this X here, right? X and Y, and they go left, right? Both X and Y into the AND gate, right? So this is part of the carry, a formula for the carry. And then separately, you need X XOR Y. So this is the XOR unit here, right? And this is what's called carry propagate, the P. That P is then fed into an AND with Z, right? So this is Z input from the side, and you get it AND, and then these two are connected from the OR gate. This is your OR gate. So this is essentially how I generated things for a cout, right? For the carry. Similarly, in the same spirit, this is the formula for sum, X XOR Y XOR Z. So this is X, Y, this is my XOR, right? And this is another XOR right here. And that gives me the sum. Okay, is everyone clear about that? I've seen one question. No, it's okay. I think I will switch to a normal thing. I would prefer to see you. I'll figure out my data later. So let's try to see more people. Yeah, if it happens again, don't run away. I'll switch to the mobile again because I switched to the permanent already. Okay, so is this part clear to everyone? Is it clear what happens with the full header? Okay. So yes, things start to get a little bit more complicated right now, but you see, it's still, there is no like rocket science here. We build things out of very primitive operations, right? Each step is clear. We had a systematic way to generate the circuits. Probably if I tell you, build a full adder and show you this picture, you will be like, oh my God, where this is coming from, right? It doesn't make any sense. It looks very complicated. But you know, if you do it step by step, it all makes sense, right? You start with a truth table, then you build these two equations by using K-maps and simplifying them using algebraic equations. And after that, it's just step-by-step building, right? And you reuse this block, obviously, the carry propagate block. Okay, makes sense? Okay, let's move on. So we just built a full adder. But I would expect you to say, well, that's really cool, but I'm not really adding 1-bit numbers in real life. I don't write programs like that. So I want something more complicated. Most of the numbers has way more bits. So a typical integer or unsigned bit, 32 bits, or remember that's architecture dependent. If you're in a 32-bit system, that's 32 bits. If you're in a 64-bit system, it's totally possible it can be 64-bit, right? The unsigned type. There is a short int, which is 16-bit, half of it. There is a long int, unsigned long int that on any systems are 64-bit, but on any system 32-bit or 16-bit. I'm old enough to work on even a 16-bit system, so I remember the old Windows that work in 16-bit mode. Right now, probably most of your laptops are all 64-bit systems. Right now, in the 64-bit system that you use, this type and the unsigned type will be pretty much the same. So Krutik, sorry if I mispronounced your first name, said we can just link adders to increase the range, right? Yes, we will. So there is a reason why we had in the side entrance, but how to build it, I will show you in the essentially next slide, right? So the goal is to get multiple bit numbers and do it such that I don't need to build this circuit from ground up, right? I want to build it from existing building block. So what do I have right now? I have a half adder and I have a full adder, right? I have these two full headers that can be used as a building block. So how are we gonna do it? Well, essentially you can think about this unit as being the build this way, and a full header being this way, right? It has one hand for the input and one hand for the side output, and it also has an output, right, itself. So that's what we want. We want to chain them up, right? It's a very basic idea. Why? It's essentially divide and conquer principle, right? If I need to build something so complicated as an adder, and if somebody is going to ever show you the full circuit for an adder, you're going to see this is not a trivial thing, right? You won't be able to build it from ground up. It's difficult. So as humans, we cannot build with such complicated things. So our strategy is to build them off of simple blocks, right? Things we don't understand. So essentially, we use each full adder that takes in a carry bit and outputs a carry bit. Each full adder can take in a carry bit, which is output by another full adder, right? That is, we essentially chain them up. And this principle, this design is called ripple carry binary adder. So the full adders chain up for multiple bit addition. So again, we start with a simple diagram. I'm not going to show you all 32 or 64 bits. That would be a very long slide. Even my wide screen, it won't fit. So I'm going to show you with just 4 items, right? Full adder units I chain together in order to perform operations on signal vectors. So conceptually, the level of abstraction that we use is we had 2 inputs, X and Y. Each of them has 4 bits. This is denoted by 4 here, right? They're all not a single bit, they're now 4 bit. Their sum is also 4 bit, and they take C in and C out, right? And this is the magical black box that does the addition here, right? And has a carry out if needed. So if we go one step deeper, what I want to do is I want to do one full adder here, 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 and here. And those are the pair of bits I had to deal with, where X0 starts with their, the rightmost bit, and X3 is the leftmost bit. This is the corresponding intermediate carries that goes from one unit into another unit. This is our input, this is our output in terms of carry, and this is the sum bits. So essentially S3, S2, S1, S0, is the sum of this vector plus this vector. Okay, and I hope the example in 4-bit convinces us I can do the same with 16 or 32, right? There's no real difference here. Okay, there is one tricky question though. Why do I have this C in here, right? Why wouldn't I use a half adder on this end? It's a tricky question, I'm telling you from the beginning. You're not expected to know it, but some of you might know it, so I'm just curious. So why do you think I don't use half and then full, full, full? Okay, a lot of good suggestions. It's like make it easier to make. You can hypothesize that to be honest, it's not a big difference because in real manufacturing, people are going to write a Verilog code. It doesn't really matter whether it's one is special or not. Something to like, so clock big shifting is not all relevant here. Good guesses, but it's not correct. Someone under the nickname L5 said something to do with overflow. That's a good guess. It's not exactly that, but it's really relevant. Yes, sign and sign, we're getting closer. I said something in this lecture. Yes, doesn't we use it for subtraction later on? So Aidan, you're absolutely correct. So you don't need to know the answer right now, but I'll show you. So this is not mistake on our side. You will see very soon, we're going to use this to do not just add, we're going to use it for subtract. So just stay with me. You will see this thing will be useful soon. Okay. So we don't use half adder because it will be very soon used for subtraction. Okay. Now, to have a little bit of fun before we finish the first half of the lecture, let's play a game with you to show how these things work. So you either need a computer or a piece of paper and a pen, right? And then again, I'm going to do this game in steps. So if at least few of you say you're done with the first step or second step, please, signal it, like do one of the Zoom features, right? clap or whatever, raise your hand, right? Saying that you're ready for the next step. Okay, let's play a game. So you should, guys, pick two numbers between 0 and 31. And I will do with you in parallel. So pick two numbers between 0 and 31. So anyone done with this step? And those numbers should be small. So don't, so that less than 31. So it would be easy to play. Okay. So, yep. Then the next step is convert both numbers into 5-bit binary form. So convert them into the binary form, 5-bit. I intentionally picked small numbers, so it shouldn't take that long to convert them. Please write in the chat when you get your two numbers converted into the binary form. I hope it's not difficult to do. So if you're done, just highlight it so I know, so we can proceed. So we had someone's ready. So any other people ready? Okay, so people with the video, that's the easiest way. Just, you know, thumb up. Yep, that's good. That works. So yes, someone got numbers. Okay, good, good. So some people got it. Okay, let's move on. Now, take the smaller number of the two and invert each digits of the smaller number. So 0 becomes 1, 1 becomes 0. So just negate each bit for the smaller number. That should be very easy to do, right? Then add up the big binary number and the inverted small binary number. So the big number, as you did it, and the inverted small binary number. Add them up, right? And when you're done with that process, right, you get some results that should be 5 bits as well. So then you add 1 to that result, another 1, just 1 to that result, and then look at the 5 lowest digits of that number. So please, if someone gets step 4 and 5, please let me know. Or if you're lost, tell me as well. I thought it. So what does 5 mean? Step 5, in step 4, you add two numbers. One big number, a big binary number, and another one small binary number inverted, right? You add them up, right? You add them up as you would do in, in high school, two numbers just in binary form. And then to that result, you add just +1. Is this clear? Oh, what does the lowest of 5 digits mean? You might, when you add up two numbers, you might get a carry on the 6-bit. What I'm saying, there's anything that will be carry over 5 bits, you drop it, you truncate it. Yep, yeah, so the last carry. So you shouldn't have more than 5 bits. The 6-bit, if it goes to the 6th digit, yeah, ignore it. Okay. So I see one hand raised. How about others? Did you guys get it to work? Yeah, so what did you get? So you just take that number, make it decimal, right? For example, I use, when I was talking to you, I picked the numbers 17 and 15, convert them and my difference was essentially 0, 0, 0, 1, 0, which really means subtraction of these two numbers. So why this funny game? Well, we get subtractions without ever doing subtraction, right? Like we get the output of these two numbers being a subtraction, but I only did additions, right? This is the cool thing about it, right? So you can get subtraction happen in, in discrete domain, and that won't work like that easily in algebra, for example, but you get subtraction just through doing this bit manipulation, right? This addition and carry, right? There's really just addition. So at the end of the day, you get subtraction without doing any subtraction. Okay, so did anyone get it? I'm just want to confirm, did it work for you? Yeah, okay, that's good. Okay, thank you. So we're a little bit over time, so that let's have a 10-minute break, and please return by 12:15, okay? Okay, thank you guys. And again, as I said, if something happens with my internet, please just wait. I will switch to a different network. Okay, thank you. See you in 10 minutes. Okay, hopefully most of you are back. And again, if people can turn on their camera again, that would be helpful. So we'll continue in 10 seconds. I know that some stuff I'm covering today might sound very basic for people that had more experience. But at the beginning of the class, I'm focusing to make sure that everyone gets the basics, right? And towards the end, we'll go a little bit faster, but right now I make sure I don't lose anyone in the course, right? So I know for some of you had more experience, hopefully it's not too boring, and I'll try to, inject some fun stuff on the way. But yeah, it's a second year course, so it's a core course, so I make sure that all of you get the maximum of it, even in the current situation. Okay, let's continue. So by playing this, hopefully a little bit funny game, we learned that subtractors are essentially just an extension of adders, right? On the computers, we can perform addition on a negative number. That's what I did on the way I'll explain you. So before we can do subtraction, we just need to understand the negative numbers a little bit. I show you how it works. Now I will explain you. So we did it a bit unusual. A lot of your classes, they show first, they teach you essentially how, some basic logic behind it, and then you do it. We did it differently. I first show you how to do it. Now I'll show you why it works, right? So it's just a little bit of reverse way. So to remind you, there are two types of numbers, right? There are unsigned numbers, where separate bits exist for the sign, and data bit is stored as the positive version of this number. You can think about them as, here is all the bit, and it's treated as a positive number, and there's a separate bit called 0, 1, signed bit. Usually when this signed bit is set to 1, that means it's a negative number, but if it's 0, it means positive, right? There is also assigned values, where all bits are stored in a so-called 2's complement negative number. And let me show you what it really means. So what is a 2's complement? That's essentially what we did. So to do a 2's complement, we first need to do 1's complement. So given number x with n bits, what we do, we take the maximum number to power n minus 1 with this number of many bits and do minus x, right? That's what we want to compute. So how we do that, we get essentially just negate things, right? So you can get these numbers in the 2's and the 1's complement by just negating all the bits. So if you had a value like that, 0, 1, 0, 0, 1, 1, 0, 1, it's bitwise not as trivial, 1, 0, 1, 1, 0, 0, 1, 0. You flip each bit, right? Very easy operation. Humans are good at those ones. And if you had a lot of ones, they all just converted to all zeros. This is 1's complement. This is what it means mathematically, right? Then the 2's complement, mathematically, it doesn't look any special. But why is it good? Because it has such a nice representation. Negation is very easy, right? You just had a huge number of inverters for every bit, and that's it. So what is a 2's complement? Oh, it's very easy. You take a 1's complement and you add 1 to it. So if you look at this number, right, this number, it's 2's complement. You first do 1's complement, you negate all the bits, and then you add 1, right? So this 1, 0 here becomes 1, 1, right, in this number. You see it. And then all 1's, 2's complement is all zeros plus 1, so it's 0, 0, 1, right? So essentially this would be useful. Please remember that. That's what 2's complement is for, right? And essentially adding a 2's complement number to the original number produces the results of 0, right? So essentially, if you had a value x and I compute a 2's complement in this precision, then this value plus its 2's complement will give 0. So it's x and minus x. The only caveat, remember, this is minus x, not exactly the same as in math, where the number of bits or the number of information you can store is infinite. It's an abstraction. This is a physical number stored in the machine. So the real minus x, it's always treated with respect to truncations of the extra bits. So essentially, the thing you need to remember, 2's complement of a plus a is equals to 0, okay? In that sense, 2's complement behaves as minus a, right? So you can think about it as minus a, right? in this, discrete math. Okay, that's what you need to remember. So I specifically put you some information here, so you would can look here on how we handle unsigned subtraction. So the general algorithm for A and B is you get 2's complement of B, which really pretty much means minus B, right? And you add these values, add this value to A, right? With the angular addition you already have. If there is an AND carry, C out is high, then the final result is positive and does not need to change, right? It means A is bigger than B, right? If there is no AND carry, so the C out is low, that means that the 2's complement of the result be minus A, right? And add a negative sign to it. So you set the sign bit high, right? So essentially that means that you set the sign bit high because you get B bigger than A. So the way to handle that, you put minus in front of it. So you send the sign bit. Okay, so let me show you the example on how it works, right? So essentially this is 53 minus 27. Again, just trust my conversions to the binary numbers. I test them with a calculator, so it should be fine. So 53 is at the top, 27 is at the bottom. We subtract them. What are we going to get? Well, the top number, A, is unchanged, right? Nothing changes to it. The bottom number, right, 27 with minus, we convert it into its 2's complement. So what I do, I flip all the bits. So this is 3 ones here, this is 2 zeros, this is 1, this is from 1 to goes to 0. This becomes 0, but then I need to add another 1 there, it's 2's complement. So that's what we get. And then you add up these two numbers, and you see the carry bit is set to 1, which means the sign bit has to be 0, right? Because it means it's a positive number. So then you just take the value as is, right? 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, right? So that's your the minus that you get, okay? Which is the value, I guess, 26 in this case, right? You can convert and check it. Carry bit is high, it means that it's positive. And this is the value 26. Now, if you try to do it in a reverse fashion, or like the negative, so you try to compute 26 minus 53. So now 27 is now unchanged. 53, right, that's its binary representation. We need, again, go into 2's complement form. And that's the value you're going to get. As you can see here, no carry bit, right? Which means the value is negative, right? In 2's complement. So you would need to set a sign bit. So if you look at the values, you see this is 26. This is minus 26. The sum is identical because it doesn't have a sign, but one has a separate bit set for sign and another one doesn't, right? So the value, unsigned value is the same, but one has this bit, one doesn't. Okay. So sign subtraction is easier. You store negative numbers in 2's complement notation, and then subtraction can then be performed by using the binary adder circuit with negative numbers. So to compute A minus B, you just essentially do A plus minus B, right? Because you just set a sign to it, right? So when you do sign subtraction, we're already signing that, then it's easy. You need to get minus B first, and that's it, right? So here I'll just show you very simple sign subtraction examples in 6-bit precision. So in 6-bit precision, and I vary the precision just, to confuse you a little bit. So you see the precision can vary. So 23, 6-bit is this, 21 is that, right? So essentially 23, minus 23 in 2's complement, that's what you get, right? And then 21 minus 23 is 11110, which is 2's complement of minus 1, essentially. Okay. Got a question? Okay, I can go quickly to the next slide. Okay, well, I hope to finish the lecture, so I need to go a little bit faster on the more simple stuff, and everything will be shared. So what's the specific question here? So essentially, what I'm trying to say, there is unsigned subtraction and signed subtraction. Signed subtraction is very easy because you just say add A and the value minus B. And the way you generate minus B, you just add a signed bit to it. So here I'm showing an example on how that theory works in practice. So when you compute an addition of 21 and minus 23, so this is the two numbers you're going to add up. This is the value you're going to get. And it looks like a lot of ones there, but if you look, because this leading bit is 1, right, it means it's a negative number. So it really means it's a minus 2 into its complement. How we do sign addition is very straightforward as well. You had 23 plus 21, and then you add them up. And that's a negative surprise for you. If you add up 23 plus 21 in 6-bit precision, you're going to get the answer minus 20. So the supposed result is supposed to be 44. I hope everyone understands that. Why does it happen? Well, that's a problem with the sign addition. It might go over the range of the 6-bit value. The maximum unsigned value you can represent with 6-bit is essentially 32, and you just go over that limit. This is called overflow. This is what happens when you don't fit in the type. This is with 6-bit, but it can happen with 8-bit and so on. So this is essentially what you need to be careful. Unsigned and signed representation both have their pros and cons, and they can have different overflows and underflows. So this is an overflow example, so you can go over the limit. So for sign subtraction, if Cout is high, it means it's negative. So for sign subtraction, essentially, yes, that's correct. So it's like what's going to happen if you, so essentially there is no such, like you don't really do sign subtraction. What you just treat the numbers as, you know, as a plus. You do A plus minus B. And if you, after that, if you happen to have a essentially a sign bit 0, then it's a positive number, right? If you get, yeah, okay. Okay, so the problem happens with the sign addition, right? Sign addition can go over the limit, right? That's the problem with the range. Okay, so that would also explain you some things that you might not understand before with the C code. If you use sign char, and char is an 8-bit integer type, and you try to add these two numbers, right? And you add them up and try to print, then sometimes you wouldn't get the number that you would expect. And the main reason is because with sign chars, right, they might go over the biggest represented numbers in this format, right? So the biggest unsigned signed number you might have in char is essentially 128, right? And it's not going to fit with this addition. So both numbers fits, but when you add them up, it doesn't. So you're going to get a negative number essentially. And then if you print it not, you know, as it printed as an unsigned value, you're going to get the value that doesn't make sense to you, right? So that's part of the problem when you're going to, like, what's going to happen is that there is a truncation happens here, the overflow. And when you print it, right, you print it, you're going to take this value and say, interpret it as a 32-bit integer. So it's going to take this negative sign and fill it with a lot of ones, right? So you're going to get a value you absolutely didn't expect. Okay. Okay, here are a few bits about the sign numbers. So the largest positive 8-bit sign number integer. So try to get what is the largest positive 8-bit signed integer. So we will gonna right now to play with you to figure out what the delta, what the difference between signed versus unsigned integer. I want to see some answers. So we see 127, and it is correct. So essentially the largest positive, what essentially happens when you had a sign integer, this bit is reserved for sign, right? The top bit. So it means I can only increase the value up until everything is ones, right? And this is 1 to 27. So it's essentially 0 followed by all ones. If I increase it by another 1, that becomes 1 all zeros, but that's not going to be 128 because it's a sign integer. What it's going to be is going to be -1. Okay. The smaller, now try to find the smallest negative. Yeah, so -28, yes, you're correct. What's the smallest negative 8-bit sign integer? Right, it's -28. So this is, so essentially, sorry, I before said -1, it's not -1, it's -128. So if you add +1 here, you're gonna get 1 and all zeros here, and that's the smallest positive negative number. So like one thing to remember that this is not 0, right? So this number is interpreted this way in the sign format. Again, this is something some of you might know from the C courses you took, but I expect some of them might not. Okay, what is the binary form for 8-bit sign integer -1? Okay, I think Sam is correct. All ones, right? So this is essentially, yeah, the value of -1. So this is, you'll get the slide so you can practice on your own if you're not sure on why it works, and then ask questions in the tutorial. And for unsigned bit number, there are 2n power possible values. So essentially the way we break out things, because we cannot break out things evenly because there's also 0 that has no sign, right? So because of that, we get 2 power n-1 negative numbers. So for 8-bit, you get it from -1 to -128. And you get 1 number less for positives. So you get from 1 to 127. Because there is also 0, right? Because you cannot break out everything evenly. So 0 goes with the positive numbers for simplicity. And essentially then there are 1 more negative numbers within that range than the positive numbers. Okay, someone's worried about the Friday quiz. Please repeat this question at the end of the lecture. We'll talk about that. Okay, so you see this thing and it's real, it's not made up. So how this happens, this is how it happens. This is overflows. So when someone built a circuit, they, didn't anticipate some conditions where, things goes with the sign up bit. That's what you're gonna get. The temperature is -28 Celsius. Yeah, might be interns, might be professionals, By the way, this story about overflows, underflows happens multiple times in history. I think one of the famous cases where they mess up the sign bits in programming one was a Boeing experiments. So the sign bit was not properly handled. When the Boeing crossed the equator, it actually thought its disposition is wrong and it turned upside down, right, to fix itself. So that's one effect. So can you imagine the people that were on this test flight that out of a sudden when they crossed the equator, the plane turned upside down and continued flying this way? Yep. And another one is, didn't the plane crash? No, it didn't crash. Yeah, so it was in a test mode, so people figure it out. Time overflow is another example, and there were several moon landings where that makes a difference as well. So this is one of the most costliest errors that happens, all these types of overflows that are not handled properly by the programmers. Another one that is the most expensive, that some people call it $1 billion thing, is the null pointer. So, but those are one of the two most common errors. Yeah. Okay. So how does subtraction units going to look like? So I'm going to talk too much about that, but essentially, as you can see here, is you can just have you know, an inverter for all the digits, right? Depending whether they're the Cin input is 1. So that's what you're going to do, and that's pretty much the full adder. And then add them. So you add them with using the XOR, right? So get into's complement, that's what you're getting. So essentially that's how you're gonna get their method subtraction from the full adder circuit. Okay. So if sub value is a subtraction is equals to 0, then it really means x plus y. So it's just addition. If sub is equal to 1, then it means I want to do subtraction, then I get x minus 1. So this circuit, based on the single input, a single bit, can be either plus or a minus. Is this clear to everyone? The beauty, obviously, that the most expensive part is here, right? You've seen how we just built the full adder, and it's completely reused, right? So only add a little bit of circuits here, right? And I get both add and sub. If you think about it, there is only one extra XOR gate here, right? And this thing has like whatever, each of that has like 7, 8 different building blocks. Even if it's optimized, it's still significant. So it's a very good trade-off. Instead of building 2 separate circuits, you just build one with some extra overhead. Any questions? Yeah. So that's kind of a beauty of optimizations, and I don't think computers at the level where they can do this manually. So it's all done by humans still. Yeah, I found it very cool that there is all the math behind it, and that's not something you're going to see in the algebra calculus class, because there everything is abstract. So there's no difference between plus or minus, it's just a symbol. But here everything has a physical meaning, so it has a cost for everything you do. And that's all real cost, right? It's some transistors that you spend on it, right? So it affects the area of your chip. The more optimally you do it, the better you're than the competitors. So essentially one circuit, both add and subtractor, so you're trying to kill 2 birds with 1 stone. Okay, let's move on. So we covered probably one of the main things I want you to remember from that part is understanding that we can build an add and subtractor, and how we can add it. It's probably one of the big fundamental things you need to learn in circuits, right? Then yes, we're not covering Verilog this time, but writing it in Verilog is not that difficult. You can look at some other slides from downtown versions of this class, see how to write it in Verilog if you want to put it on a real chip. But you pretty much learn all the most interesting, tricky parts, right? How to build an adder of any scale. Now you can easily estimate how complex this adder can be, depending on 32 versus 64-bit you want to do, right? And you will see how to do subtractor. And obviously now you can think about multiplications and more complicated things that I'm not going to cover now, but you can feel like they can be built with the same basic principles, trying to utilize the existing logic. Okay, now we're trying to look at the decoders. So what is the decoders? I think a lot of you heard this word, but what does it formally mean? It usually means you take some cryptic input that has certain number of bits of information and that convert it into some meaningful information. For example, you might have a 5-bit input encoded original information, and that's decoded information. That's what decoder does. It is some magic logic that takes a cryptic input and converts it in something that makes sense to the world. So decoders are essentially translators. They translate from the output of one circuit to the input of another one. So the number and the example is a binary signal splitter that activates one of the 4 output lines based on the 2-digit binary numbers, for example. Yep. So just be careful. I'm going to mention there is some difference from what I'm going to say here with the lab too, so you don't get confused, right? So conceptually things are similar, but just don't misinterpret things. Binary signal splitter activates one of the 4 output lines based on a 2-digit number. So for example, if I want, say ABCD would be 4 different colors that can highlight on the other end. I want to kind of tell which light I want to encode. So decoder would take 2 bits of information, because to know which one of the 4 is needed, I just need 2 bits of information. So the decoder would transform these 2 bits into which color they highlight. If you're ever going to play with real hardware, everything is done through different decoders, right? So we already, one of the examples of decoders are demultiplexers, right? So they're related to decoders. They essentially does multiplex operations in reverse, right? So you take the cryptic output and then convert it into proper input. So essentially, multiplexer chooses one from multiple inputs as outputs. Demultiplexer is the other way around. It takes one input. It's one input chooses from multiple outputs. And this is the examples that becomes closer to your lab. So a 7-segment decoder. It's common and useful decoder application. It translates a 4-digit binary number to the 7 segments of a digital display. And each output segment has a particular logic that defines it. For example, you see all the segments here, right? So the segment 0 activates for values 0, 2, 3, 5, 6, 7, and 8, right? And this is in binary format. What does it mean? So this is essentially how we can define a k segment decoder. You do it for each segment. As you can see, it has a lot of things where it's defined. So the best way to handle that, you need k-maps, right? We learn it on purpose. By the way, guys, if I'm too fast, the best way to handle that is turn on your video, right, and show me that you're show me your puzzle face, and I know I'm going too fast. So just note that what we talk about here is not exactly the same as what we do in lab 2. In labs, we translate numbers 0, 1, 3, 5 to displayed letters, such as H, E, L, and so on. This is specifically defined for the lab. Here we're talking about translating 0, 1, 2, 3 to displayed 0, 1, 2, 3, 4, right? That's the difference. This is a more common use. For 7-segment decoders, turning a segment on involves driving it low, activate low. So assuming a 4-digit binary number, segment 0 is low whenever I had an input mentioned here, and high whenever input number is the opposite, 0001 or 0100. We then create a truth table and map like the following. So essentially, if I want to build a decoder for this segment, just for simplicity and to save time, I write you the truth table for it. This is your 4-bit inputs, and this is essentially, those are the ones and the positions that matters, and this is the other ones that are zeros. I think the basic principles are not just for those displays, but yes. So it is a generical principle in general how you build this decoder, is not specific to anything, but yes, you can use it for ANOT displays, for example. Yes, you're correct. Okay. So what we're going to do is this. So there are a couple of things, right? You notice that it didn't write you the full table, right? Why is that? Because the 6 rows on the values from here to here is not defined. How does this happen? Why this truth table is not fully defined? Well, it turns out when we select 4-bit, we don't have that many states possible. So there are states that essentially deprecated and missing, right? What does that mean? Well, when we're going to try to define the circuit, we're going to write in K-map form, right? So this is x0, x1, this is x2, x3. This is how we're going to write it. And there are going to be 6 states that doesn't exist. How this happened? Well, we only had 10 digits, right? And 4 bits means 16 possible states. So these 6 states are not possible. How are we going to use that information that's not possible? Well, the good part for us, is that we can do circles around what we built here, right? So that would happen, but it's not optimal. Why? Because if something is not defined, the beauty of transistors, it means I can define it any way I want. So if I want it to be 1, I keep it 1. If I want to be 0, I can keep it 0 because it's undefined. If the variable is undefined, I can treat it any way I like. So if I'm going to just do it without looking into those axes, I'm going to get the representation. So it's going to be 2 isolated zeros. So I'm going to get, them in their, mean term form. So I'm going to get 2 terms. But if I'm actually going to take and use those don't care values, so then I can record them any way I like, as I said. So essentially, if it's convenient for me to make it 1, because remember, the larger this box is, the more efficient is representation, the better it is for me. So you see here, the hex 0 is going to have this representation where 1 term is optimized. So this is the new thing to you. Before, you always seen the truth table that would be completely defined. But remember, we had built certain things where it's not always needed. So this is the trick you can do. You can say, why we didn't define this to be 1 and 0? Well, we don't want to define because we don't know what would be useful. In another case, that might be useful to be 0, or that might be useful for this to be 1. So we don't restrict you, call it undefined. And then whatever use case you want to use it, you defined it the most convenient way for you. Okay, that's a very common trick used in circuits and programming in general. So boxes can cover axes or not, whichever way you like, to build a more efficient representation with schemats. Okay, we can do exactly the same trick for segment 1. So see, in segment 1, you had 1 here and 1 here. What we're going to do, yes, we're going to use these 2 extra axes here. And then representation of hex 1, right, is going to be consist of addition of 2 terms. Each of them consists of 3 elements, right, connected with AND, 2 mean terms. But you see, they both are optimized. So you make it more efficient than if you wouldn't without the AND-def trick. Segment 2, what we're going to get here? Well, we can do this. So that would become just 1 term here. So, okay, so I guess I tried to cover, so that I start with the final questions first. Wait, why are some of those undefined? You had only 10 digits from 0 to 9, right? You try to encode them. So when you try to encode them, you pick the minimal possible number of bits that covers that. So the number of possible bits is 4, but the 4 bits cover 2 power 4, 16 possible encodings, and you only need 10. So you use the first 10 and the other 6 are not used. Okay. Okay. Farhan, does it answer your question? So essentially you get up with 6 states that are not defined, right? What I'm showing it, we shouldn't just forget about them or treat them like we can treat them any way we like, and we make them 1 when it's convenient for us, right? So that allows us to make a more efficient representations of the circuit. And I think Krutik asked the questions. So this is just the notation. I just call this circuit hex 1, 0, 1, 2, and so on, right? We don't really use the hexamal notation. Okay. Okay, so the final 7-segment decoder will look like that. Remember, it's gonna have these 4 inputs, right? And it's gonna have, I only show you 3 of these, how they built, right? But you can imagine how you're gonna build all of the other ones as well, right? So the decoder can be actually quite complicated. And it's gonna convert all this, encodings that you use into the actual, information to highlight, the digital clock or something like that, the single digit, okay? So decoders really all look absolutely identical. They all look like, here is my number of bits, and this is like how many bits I need. And there are tons of outputs. So it looks boring from the outside, from the complexities here, right? What this logic really means. So all decoders look like a box, right? But all the logic is here. So based on these inputs, you figure out how to invoke this and how to invoke this and how to invoke this. So they may be actually quite complicated. Okay. Any other questions? Okay, let's move on. So again, so this is, we covered encoding, decoding. So essentially it might look complicated, but again, remember the beauty is divide and conquer approach, right? I don't try to build this whole thing from scratch, right? I take and build from this input into the first output, from this input into the second output, and so on, right? Okay, so comparators. So I guess this is one example of comparison here. Find the differences between the two figures. So this is what conceptually comparators are about. So comparators is a circuit that takes into input vectors and determines if the first one is greater than, less than, or equal to the second one. I'm pretty sure when you write something in C and you write an if statement with a condition there, that's a comparator. So that map into some assembly instructions in the end, and that would make a comparison. So the question we pose right now, how does one make this inter-circuit, right? So one question to you, again, just to, I know it's the end of the second hour, just to test how your brain works. What is the trivial way to implement comparators? So like, what did we build already that would easily allow us to build comparisons? Don't be shy, like type your answer. Not max, subtraction, yeah, yep. So the most trivial way to do it is to do subtraction, right? You just subtract two numbers and you look at it. Why we don't do this just from that and close the topic? It can be an overkill. You would see that comparators can be done better, but at some point the complexity of building it from the design perspective might become so large that for larger numbers we might just say forget it and we just use subtraction. But for small numbers that actually makes sense, and I'll show you why. And it might not finish today, then we will continue on Friday. So, but I want to start today. So what the basic comparators is, no surprise, we're going to start with one bit, similar to with addition and subtractors. Consider two binary numbers, A and B, where A and B are just one bit long. What the circuits would be for the basic comparator unit. And we want to build one that would cover all three cases, right? A equals B, A larger than B, A smaller than B. So how we build it from a truth table, right? That's the easiest one. So let's look at the truth table A equals B. So essentially you can have 0, 0, 0, 1, 1, 0, 1, 1. So the logic for A equals B is essentially when both are equal, right? So when you have 0, 0 or 1, 1, right? So if you look at that, that essentially, I'm not going to write K-maps or anything that's quite trivial here. So it means AB plus not A and not B, sorry, AB and not A, not B is this, right? This is essentially the representation of that. How about A bigger than B? You just look at it. And the only time when it happens, right, A strictly bigger than B is when essentially A is 1 and B is 0. So it's A and not B. And A smaller than B is not A and B. Yeah, you're asking the right questions, but we will get to that. Just wait a second. So let's not optimize it. Let's first understand what it's logically doing from the truth table, right? Okay. So essentially, the basic comparators, right? The outputs. So this is one bit, and there, as someone said, that can be replaced with XOR or something like that. The thing about XOR, it doesn't really make things that much simpler in this case because XOR is more complicated than other circuits. Okay, basic comparators. So this was one bit. One thing you can probably notice, this thing is much simpler than if I do a subtraction, right? Subtraction would require to me to build either a half or a full adder and then add it with an extra logic to do subtraction, right? That was clearly would be much more complicated than just one and a not, right? So this thing is much simpler, right? So this is what I want to highlight. How about 2-bit comparators? Well, that gets a little bit more complicated now, because if I look at the logic, what does it mean to be equal, even? That becomes more complicated. So first of all, for the 2-bit variables to be equal, it means that it has to be two conditions true at the same time, right? So in the first condition, it's you either have the first two bits equal to 1, and the second two bits at the same time has to be, or there has to be both equals to zeros. Or in other combinations would be the second two bits is ones and the first is zeros. So if both are true at the same time, that would give me A equals B, right? So that makes sure that the values of bit 1 are the same, and that means that the values of bit zeros are the same, right? So it essentially looks at all possible combinations on when these things can be zeros, okay? If you want to check A is bigger than B, I'll just show you there, the logic for it and explain it, but you see it already gets quite complicated. Why is that? Well, first of all, I need to check if the first bit satisfies the condition. So for example, if I want A bigger than B, then if the top bit, the most significant bit, A1, is bigger than B1, which means it's 1, and B1 is 0, then that's it. It already means that this value is bigger. Otherwise, if it's not, and not is written this way, right? If it's not, then you need to check that that the first bits are equal, right? And then it's and then you can compare the bottom bits. So essentially, the way to read this long expression is, how come A can be bigger than B? Well, the first answer is if the leading 2-bit values, A and 2-bit values B. It means that, first of all, A has a leading 1 and B has a leading 0, then we are done. If not, then we're checking that they're both 1s or both 0. And then, if that's true, then I can look and do a 1-bit comparisons for the latter bits. So for example, you can have both starts with zeros, and then to A to be bigger than B, it needs to be that A0 is 1 and B0 is 0. Then it's still true. So you start with the top bits. If it's bigger, then you're done. If they're equal, you keep continuing, right? And they're absolutely symmetrical for A less than B. So that's essentially this logic here. To A to be bigger than B, it's if and only if A1 is bigger than B1, or A1 equals than B1 and A0 is bigger than B0. And essentially, using the same principle, you can make a very complicated comparators, right? The main problem why people don't doing that is because, as you can see, the complications, even with 2 bits, it's already hard to parse it. If you're going to think about 32-bit values, well, I'll just show you, I guess, just skip over some slides. So things starts to look like that on this circuit here. So people sometimes just give up, say, you know what, I'll just do subtraction, just don't waste the engineering time. Remember, when I say easy, it's easier for you as the developer of the circuit, right? It might still look crazy complicated, but it might run faster, right? But at some point, engineering time is more important than the runtime. It's very hard to design it correctly. It might be not scalable. Changing the circuits is very difficult. So people just go for a less optimal, but more easy to engineer and optimize solution. And I think we covered enough material. I'll finish the comparators on Friday tutorial, I think there was a question about what's going to be quiz on. Similarly to what we did before, it's most of your quiz is going to be on the previous week, but some of their, questions might be covering this week as well. So essentially, anytime you come to the quiz, you're responsible to everything that you learned before, right? And pretty much it's mostly focused on what you learned and already played with in your lab, plus a little bit of the content of today's lecture. Okay, does it answer all the questions? Okay. Yeah. Okay, any other questions, guys? I know it gets a little bit more complicated towards the end, but don't worry. The main thing I want you to understand is the key principle of how we design things, divide and conquer, right? The way we build adder and chain it up. This is something I really want to remember from this lecture because it's important. It's the principle you're going to use a lot in both building circuits and in general in engineering. Building something that is tractable in complexity by humans. That's the only way we can build very complicated software and hardware designs. It's a very common principle in general. Okay, that's everything I have today. Any questions? The lab 3 is already prepared. It will be probably posted sometime today. I just need to review it, but Tia already prepared. So it will be posted soon. You'll get enough time to do it. So it's either later today or early tomorrow. Any other questions? Okay. If there are no questions, then thanks a lot, guys, and sorry for the networking glitch that I had today. I see you on Friday. Thank you, guys.